Hello, it's a pleasure to be with you today, and I'm going to talk about the role that biochar can play in our urban communities, specifically as it relates to rebuilding the soil carbon sponge to address stormwater and its impacts. The years of rapid growth and poor land use practices has resulted in a number of environmental challenges, including flooding, droughts, water quality, groundwater recharge, urban heat islands, and of course climate change. In the U.S., much of our infrastructure has exceeded its intended lifespan, opening up opportunities to innovative ideas such as the use of biochar. We need to remember that new infrastructure will have a planned use of 50 to 100 years and must be designed with climate change in mind. The impacts, scale, and costs associated with managing stormwater in our urban environments will be enormous. Recent EPA data indicates the U.S. has nearly 28 million acres of impervious cover. In addition, there is also an estimated 40 million acres of turf. To address the years of environmental impacts, the EPA has mandated via stormwater permits that urbanized communities must manage and treat the water coming from the impervious areas. For many communities, this is a huge challenge and expense, with EPA estimates in the range of $250,000 or more per impervious acre to treat and manage. Innovative and cost-effective solutions such as biochar can provide a win-win opportunity. With over 40 million acres in the U.S., few would know that grass represents our largest agricultural crop. In the Chesapeake Bay region where I'm located, we have seen a tripling of grass to nearly 4 million acres since 2009, representing 10% of our total watershed area. The millions of acres produce a significant amount of polluted runoff each and every year. This polluted runoff is a result of highly compacted soils, fertilizers, fossil fuels, and irrigation water. This amount of unused grass areas offer tremendous opportunity for biochar to assist communities in meeting their EPA stormwater requirements. Often when we see green yards and fields, we immediately assume that they have the ability to infiltrate and store rainwater. However, in most cases they provide little infiltration or storage and are often just as much a contributor to runoff and pollutants as the impervious areas. While receiving little attention to date, turf offers a tremendous opportunity to become part of the solution through an aggressive urban soil carbon restoration program that can provide numerous environmental services while saving communities millions of dollars and meeting their EPA stormwater permit. I'm going to go out on a limb today and assume that stormwater and green infrastructure might be a new topic for many. As with any industry, we have buzzwords, acronyms, and definitions. Two that should be explained include green infrastructure and hydro modifications. Green infrastructure is the latest buzzword related to stormwater management around the country. Basically, the approach is to manage stormwater runoff using natural systems and/or engineered systems that mimic natural systems. The objective is that by using distributed green infrastructure, urbanized watersheds shown primarily in scenarios B, C, and D in the slide can be restored to mimic scenario A, woods, meadows in good condition. In order to achieve this objective, the project must first maintain pre-development runoff characteristics of either a meadow or woods in good condition. This is usually computed through hydraulic modeling, maximize disconnection of impervious surfaces, and use many small non-structural treatment systems. As our environments become more impervious, the natural hydrology of the watershed is modified, increasing peak flows, runoff volumes, and generating flashy flow events. For scenario D, which is nearly all impervious, much of the runoff flows off the landscape into storm drain systems as fast as possible to avoid flooding. Without the vegetation, evapotranspiration declines, and little to no infiltration occurs, eliminating groundwater recharge and natural cooling effects. Scenario D is extremely complex and expensive to retrofit, with little green space to work with. This environment relies heavily on engineered media and structural systems, such as underground storage, tree wells, green roofs, pervious pavement, and pavement removal to reduce runoff. As part of this presentation, I will focus on scenario B and C as the primary opportunity in scaling up biochar in the urban environment. While there are a number of ways biochar can be integrated into scenario D, as some grease spaces do exist on a limited basis, that will have to be for another time. Let's now transition to discussing biochar as part of a stormwater management strategy. In the beginning, much of our biochar efforts were associated with the enhancement of engineered bioretention media for bioswales, bioretention basins, and rain gardens. In 2012, working with the University of Delaware, we began to evaluate the potential to modify soils in situ to mimic what we were finding in the biochar enhanced engineered media. In 2014, the research team received an EPA and a Transportation Research Board grant to study the potential benefits of amending soils along highway greenways. The pilot areas were very small, capturing runoff along a 3-lane highway with two 6-foot by 20-foot treatment areas. A third area just captured roadway runoff. Both treatment areas were tilled to 12 inches or 60 centimeters, with one being amended with 4% by mass wood biochar. Each test plot captured the same amount of impervious area. After a year and a half of data collection, the study showed significant peak and volume runoff reduction. The biochar amended soils provided an average of 77% reduction in peak flow, while the volume was reduced by about 53%. For peak flow attenuation and runoff, tilling provided very little benefit as compared to the addition of biochar for the sandy loam soils. As would be expected, study results will vary based on soil types. Currently, the University of Delaware is working on a soil biochar model to better determine the amount of biochar to be used and predict how it would respond in a given soil. An exciting aspect of the study, based on data collected from 84 storm events, was the ability to capture 100% of the runoff from 85% of all the storms that occurred during the study by amending just 12 inches. An interesting finding from our efforts was that only 9 inches of the amended soil were actually being used to capture the majority of the storm events, and only during bigger storms were using the remaining 3 inches, which then became surface flow. This was discovered during a mass balance quality control check and confirmed using multidimensional flow modeling by an independent team. One of the coolest findings during the study was the effect of biochar on soil temperatures. The addition of biochar into the soils helped to meter the overall soil temperature extremes. Based on literature review, it appears the soil temperature metering may be due to the combination of increased water holding capacity as well as microbial activity. The results indicate the soils warm quicker and cool slower, temperature extremes are limited, more extremes can be found in the spring and summer than in the fall and winter. Upon completion of our first highway pilot project, efforts moved to the installation of larger demonstration projects, primarily along highways for a variety of transportation agencies. The I-95 Toll Plaza project was recently installed for the Maryland Transportation Authority, led by the University of Delaware and construction partners this past summer. As part of the effort, means and methods for installation as well as material specifications were developed. Lessons learned from previous installations incorporated a number of additional steps. One such critical item or step is that biochar must be moistened and allowed to absorb water prior to tilling into the soil, or it will not incorporate evenly throughout the entire soil profile and primarily remain on the top. Adding the moisture also helps reduce biochar dust, which is critical for safety, especially along busy highways such as I-95. The other change we made as we began to scale up operations was the use of a specialty harrow tiller. Most rotary tillers can only go down 4 to 6 inches and will pull up a lot of rocks. The power harrow is able to get down to 11 inches and minimize the exposing of rocks while blending moist biochar into the entire soil profile. The Haro made the installation process go quicker and provided for a cleaner final product. To date, the largest biochar project we have done was the conversion of a third of an acre of grass to an infiltration basin. Within the basin, the soils were amended down to 2 feet to better capture runoff from an 8-acre drainage area with a 3-acre parking lot. In order to get the highest performance credits, the amended soils needed to function more like an engineered bioretention media, which averages 80% sand, and have it infiltrate without the use of underdrains. To gain additional credits, rather than putting the site back to turf, we chose to take a conservation landscape approach and convert to a meadow. This fall, we plan to come in and complete the pneumatic soil decompaction, injecting biochar to a depth of 4 feet within the meadow to further increase infiltration. For the remainder of the turf within the drainage area, the pneumatic soil decompaction will be done over a 3-acre area on a 6-foot by 6-foot offset grid. The project is heavily instrumented with a complete weather station including rain gauge, relative humidity, temperature, wind, speed and direction, evapotranspiration, and solar intensity. Groundwater surface wells were installed to monitor the rate of storage as well as time to completely infiltrate. The soil moisture and temperature probes have been installed at 6 and 12 inches, both in the amended and non-amended soils. The University of Delaware will continue to work with the partners by conducting field measurements pre- and post-installation and treatments, and will be working on a watershed scale model to allow for better predictions of the hydrology modifications as a result of the project. As we continue to add to our project experience, we have been experimenting with installation processes to cover a variety of situations and of course make it as efficient and cost-effective as possible. As it relates to treatment and equipment usage, there are 3 primary techniques currently being employed based on the amount of water management we're targeting. Surface treatment for non-hotspot areas uses a very common turf management strategy to increase infiltration, aeration, and turf health. It is recommended that biochar or a blend of biochar compost fertilizer be spread after aeration. This is important to consider to ensure that the turf remains an even color and thickness throughout the site. This treatment allows for more infiltration, water holding capacity, and nutrient management right at the root zone. To infiltrate larger storm events, like a 2 to 5 year event, then the deeper Haro tiller must be used. On most projects, the average amount of biochar has been 4% by mass, but we are currently testing effectiveness of using only 2% by mass to see if we can get a similar result for less cost. Depth of treatment can also be easily adjusted with the Haro and makes quick work of soil amending and turf replacement. Lastly is the pneumatic soil decompaction technology. This is a great method to cover large areas in a non-destructive manner. It is also the best approach to really capture large volumes of runoff from very large storm events above 5 years. As shown in the call-out box, we can inject small quantities of biochar into the soil at 3 feet, 4 feet, and 6 feet in depth, depending on soil characteristics, groundwater, and bedrock. Heavy, finer grained soils are a bit more challenging. The goal of the biochar is 1. To serve as an aggregate or similar to fracking sand to keep the fissures open for water and air, and 2. Promote aggregation via mineral or bacterial or microbial activities. Other amendments can also be incorporated as desired, such as dry seaweed, fertilizers, and inoculant materials. I'd like to see if I can get a video to play so you can see the equipment in action. Let's give it a little bit of sound. Get the real effect. As you can see, the ground lift up at that point after the air was injected. As part of our work, Let's now take a look at how scaling up biochar and urban soil restoration can have a major impact on a larger watershed scale. At this time, we are in the early stages of scaling up from pilot and demonstration projects. So obviously, the more projects we get under our belt will yield more data on the effectiveness of urban soil restoration practices. However, based on what we have learned to date, we can take a hypothetical view using similar modeling studies to evaluate biochar's influence beyond a pilot site level. A recent paper by Fry and Maxwell provide a similar framework to look at the potential benefits of a broad-scale urban soil restoration program. In the original Fry and Maxwell study, existing poorly drained soils were removed and replaced with sandy loam mix. Our evaluation took this approach and modified the data, assuming in the addition of 4% biochar treating 15% pervious area. We are At a site level, impervious disconnection is paramount to achieve runoff objectives. The research models have demonstrated that the most effective practices include downspout, sidewalks, and driveway disconnections, deep soil decompaction, and green patches often found between the road and sidewalks. Additionally, most houses are graded to drain toward the public roads, thus increasing the volume of runoff that has to be managed by community infrastructure. Thus, short-circuiting those flow paths will have a major impact on the total runoff from the site. Studies have also shown that most individuals do not want to give up their grass for green infrastructure practices like bioretention facilities, rain gardens, or even conservation landscaping due to maintenance and loss of space or the perceived loss. Yet, for municipal engineers and regulators, these green practices are the primary tools for on-lot treatment. Additionally, considering the majority of the available land is privately held, there is no way to mandate their acceptance. Access to these private properties can be difficult, and so more innovative approaches are needed to gain access to these areas, like maybe a stormwater fee elimination and/or a subsidy/tax credit towards a brand new yard. Investing in increasing the ability of a lot to infiltrate and hold more water through the incorporation of biochar has shown great promise at a smaller scale, and we have no reason to assume different results when scaling up. An additional selling point to landowners and community leaders are all of the other benefits, including reduction in water usage, waste upcycling, carbon sequestration, microclimate temperature management, contamination capture and treatment, and nutrient management. Now combining Based on the results of the hypothetical analysis, the use of biochar in urban soil restoration can provide treatment of 8+ acres of impervious area to every 1 acre of biochar amended soils. Assuming the treatment of only 15% of pervious area in the right location at critical hotspots would cost between 2 to 3 million. Pneumatic soil decompaction and full yard treatment would be an additional cost. By comparison, using the EPA's $250,000 per impervious acre treated, the community would be looking at over $8 million using green infrastructure systems such as bioretention basins and rain gardens that most homeowners do not want to have on their properties. This price doesn't include the long-term operations and maintenance costs. As with any new approach, prices are generally higher at the beginning. Currently, much of the costs are tied up in biochar and transportation. This is due to the lack of production in different regions of the U.S. If biochar production could be scaled up regionally, it can be assumed that the prices of installation would come down in the cost per gallon stored or treated. Currently, the University of Delaware are working on developing a reliable hydrology model that is able to predict the influences of biochar on a larger watershed scale basis. In closing, the opportunity for scaling up biochar on a national level is enormous. I have focused heavily on stormwater markets as a lot of money is being allocated to meet the EPA's permit requirements. The environmental benefits for communities having to meet these requirements are immediate and offer considerable cost savings over other stormwater management practices. Communities that invest in an urban soil carbon restoration program can avoid having to acquire property from private citizens, squeeze more out of what the community already owns and has access to, better adapt to climate change impacts, and protect against long-term inflationary O&M costs. One aspect that is guaranteed when implementing this type of program is that there is always and always will be grass farmers interested in tending to the community's newest stormwater practice, whether they recognize it as one or not. Various techniques or treatments to maximize soil rebuilding benefits with a major focus on water capture.